So the first problem that we have is problem 3.52. This statement and the figure is in front of you on your screens. The statement reads that water flows through the pipe contraction shown in figure 3.52 for the given 0.2 meter difference in the manometer level. So this is the given 0.2 meter difference of the manometer level. Determine the flow rate as a function of the diameter of the small pipe D. So we have to find the flow rate as a function of this dia of this small pipe. Uh, this problem is related to the Bernoulli equation. So we select 2 points to apply Bernoulli equation. The points are now on your screen. Point 1 and point 2. Point 1 we have taken to be in the center line of this pipe, just below this first manometer, and point 2 we have taken just at the entrance of this second manometer. Remember, this point 2 is a stagnation point. So we apply the Bernoulli equation between point 1 and 2, that's written in front of you on your screens. We can see that easily that the height z1 is equal to z2 in the Bernoulli equation. Also, velocity v2 at point 2 will be 0 because because point 2 is a stagnation point. So our Bernoulli equation with these simplification becomes P1 over gamma plus V1 square over 2G is equal to P2 over gamma. Um, but we know that P1 over gamma, we don't know this height actually, this height of this point from the center line. So we assume this to be X. Let me just draw this X over here. So this length is actually from this center line to this point, this length is actually X, and this P1 over gamma is equal to X, and then we define uh, P2 over gamma to be X plus 0.2 meters. So with this, we write our Bernoulli equation again, or we put these values of P1 over gamma and P2 over gamma back in the Bernoulli equation, and we have X plus V1 square over 2G is equal to 0.2 meters into X. So then we have V1 is equal to under the root of 2G into 0.2 meters, and V1 comes out to be 1.98 meter per second, and Q, now we know that Q is equal to A1 V1, and Q comes out to be 0.0156 meter cube per second for NED. So doesn't matter how much the dia is, this flow rate does not depend upon this dia of this small pipe. It's constant, and this is 0.0156 meter cube per second. Then the next problem that we have is problem 3.80, and it states that if the viscous effects are negligible and the tank is large, determine the flow rate from the tank shown in figure P3.80. So we are being shown a tank. We are being told that the upper 2 meters of fluid in this tank is an oil which has a specific gravity of 0.81, and then we have 0.7 meters of water, and at this height of 0.7 meters of water we have a outlet which is 50 millimeters in diameter, and we are being told that we can neglect the viscous effects and we have to find out the flow rate out of this tank. So we will take 2 points, points 1 and 2. We will take point 1 to be just at the surface of the water, and point 2 to be at the exit of this pipe, which has a diameter of 50 millimeters. We'll write Bernoulli equation between these 2 points. Remember, to apply Bernoulli equation, we have to assume the flow is steady. We have to assume the flow is incompressible because this is water, so we can, and we are applying Bernoulli equation between points 1 and 2, so we can assume this to be incompressible because this is water. We have to assume the flow to be inviscid, and we are being told in this problem that we can neglect viscous effects, and we have to assume that the points 1 and 2 lie along a streamline. So we write Bernoulli equation between points 1 and 2. um, P1 we can find out through fluid statics. We know that if the surface pressure at the surface of this oil, at the free surface, is P naught, then P1 will be P naught plus gamma of oil into H. We take P naught to be zero gauge, since this is this will be atmospheric pressure because this is open to atmosphere. So P1 will be equal to gamma naught into H, where H is equal to 2 meters. And so now we put in the value of P1 in the Bernoulli equation. V1 we take to be 0 because we assume that the tank is sufficiently large enough, and this surface of water, it moves very slowly. And P2 we also take to be 0 because this jet exits into the atmosphere, and the pressure of this jet will be equal to the atmospheric pressure. So with this we have V2 is equal to under the root of 2g into gamma naught H over gamma plus Z1. Gamma naught over gamma, or this is gamma oil over gamma, which this gamma is of water. This is actually specific gravity of the oil, which is 0.81. We are being given this over here in this figure as well. And then we can find the flow rate Q is equal to A2 into V2. We can calculate V2 by putting in the values, and area A2, we know that at 2 the diameter is 50 mm, so we convert this 50 mm to meters. This is pi by 4 of 0.050 meter square into velocity V2, and this comes out to be 0.0132 meter cube per second. So the next problem that we have, this is a very interesting problem. Uh, an ancient device for measuring time is shown in figure 3.94. You might have seen devices like these in movies or cartoons. The axisymmetric vessel is shaped so that water level falls at a constant rate. Determine the shape of the vessel. R is equal to RZ, which is that determine R as a function of this height Z. If the water level is to decrease at a rate of 0.10 meter per hour and the drain hole is 5.0 millimeter in diameter, we are being shown over here as well that this drain hole is 5.0 millimeter in diameter. The device is to operate for 12 hours without needing refilling. Make a scale drawing of the shape of the vessel. So we have to draw this shape of the vessel, or we have to uh, find out R is equal to R is a function of this height Z. So we take 2 points, one at the surface and the other one at this outlet, which is 5.0 millimeter in diameter, and apply Bernoulli equation between these two. Remember, we assume the flow to be quasi-steady. This means that this is really not a steady flow, but we assume this to be steady flow. To apply Bernoulli equation, this is a must, but we cannot apply Bernoulli equation to an unsteady situation. So we are assuming this to be steady. We are assuming that points 1 and 2 lie along a streamline. We are assuming this to be in viscid flow, and we are assuming this to be compressible. This is water, so com compressibility, incompressible is not a wrong assumption over here. Also, since point 1 and 2 both are at the in the atmosphere, so we assume we say that P1 and P2 are the pressures P1 and P2 in Bernoulli equation are zero gauge. Uh, the height Z1 we take to be equal to Z, which is unknown to us, and the height Z2 we take to be we take point 2 to be datum, and Z2 is equal to 0. Thus, with this information, our Bernoulli equation comes out to be this. We have just velocity v2 and v1 over here, and if since we know that v2 or the velocity of this surface will be very slow, we are being told over here as well that this is 0.10 meter per hour. In comparison to v2, v1 will be very less, so we will take v1 to be 0 over here, and we'll find v2 to be under the root 2 gz. So now we'll use continuity equation between point 1 and point 2, and we know that the velocity v1 of this surface will be is equal to dz over dt, which is actually the how quickly this height is changing. So we are given this velocity v1 as 0.1 meter per hour. We convert this to meter per second. So this v1 comes out to be 2.78 into 10 to the power minus 5 meter per second. Now we put in the value. So area at 1, we don't know the radius at 1, but we take this to be unknown as r. So the area at 1, the cross-section area at 1 is pi r square into the velocity v1, which we have just calculated. Area at 2, we know the diameter of at point 2 is 5 millimeters. So the area 2a2 is pi by 4 into 0.005 meter square, and we have just calculated v1 using the Bernoulli equation in the last slide, and we put that over here. So and r and z both in this equation are in meters, and with this we have a function for r is equal to 0.9980 raised to the power 1 by 4. So this was the required function that we needed. We needed to determine r as a function of this height z, and we have calculated that. We have also plotted this over here, the z, the variation of the radius r, which is this radius of this vessel with this height z. So this shape has also been plotted over here, and on the right side we have or. So this tells us that how the time will change with the height or the level of water in this vessel.